For a century, mathematicians have pursued the Hilbert-Polya conjecture. This is the hypothesis that we can find a specific geometric space whose spectral eigenvalues, its natural resonant frequencies, map exactly to the zeros of L functions, which are mathematical tools that encode the distribution of prime numbers. To test this hypothesis rigorously, we turn to the Poincare homology sphere, also known as S3/2I. This specific shape is the most arithmetic compact manifold that exists. It earns that title because its geometry carries the E8 character structure. E8 is an exceptionally complex mathematical symmetry group that packs the maximum possible arithmetic density into a physical space. By isolating the problem here, we establish a strict boundary condition. If any compact geometric space possesses the mathematical machinery to spectrally read the Riemann zeros, S3/2I must be the one. Yet S3/2I delivers a precise negative result, captured in the Chateau-Le Chateau theorem. The geometry of this space reads arithmetic structure with flawless precision, but is mathematically barred from ever pinpointing where the L function zeros actually sit. This diagram illustrates the root cause of this barrier, a concept called curvature duality. The equation governing the positive curvature of this space dictates both its physical properties on the left and its arithmetic properties on the right. Here we encounter a direct contradiction. The exact geometric mechanism that strictly prevents us from spectrally accessing prime numbers is the exact same mechanism that allows physical matter to have mass. To understand why the Riemann hypothesis resists a spectral proof on this space, we have to deconstruct how a single positive curvature equation enforces an impenetrable divide between physical reality and arithmetic accessibility. This scatterplot maps out the manifold's two baseline capabilities for reading L functions, comparing selectivity against domain. S3/2I acts as a perfect arithmetic mirror, but early attempts to read its reflections forced a severe trade-off. First, we plot the Reidemeister torsion, which is an analytic tool that measures the geometric twist of a space. Torsion achieves maximum selectivity by factoring exactly into just 4 L functions, but it only functions at a single point, where the input parameter s equals 0. Next, we plot the Dirac operator, a mathematical function used to describe fermion fields. The Dirac operator covers the full complex strip across all values of s, but it suffers from minimum selectivity, sweeping up dozens of overlapping arithmetic characters at once. To break this trade-off, we apply a mathematical technique called character table rotation. Specifically, we use an invariant known as the C2 equivariant eta. Notice how the C2 transformation merges the extremes into a single line, governed by a precise closed-form equation. This operation successfully isolates a single Dirichlet beta function, a specific type of L function, across the entire complex plane. Because this manifold can isolate individual L functions at any arbitrary value of s, we know it possesses the complete, perfect spectral data of the primes. This creates an immediate mathematical tension. If s cubed over 2i isolates the beta function at all values of s, why does it systematically fail to locate its zeros? Look at this complex plane comparing the actual vertical critical line of roots against the geometric curve generated by our isolation equation. The equation gives us beta of s equals beta of s minus 2. This equation defines what we call a coincidence barrier. It maps out a curve where two shifted beta values happen to match, but it tells us absolutely nothing about where the function actually vanishes to 0. The structural truth is that spectral eigenvalues on this manifold produce relations between shifted L values. These relational data points are entirely different geometric objects than the roots of individual L functions. We cannot bypass this issue by swapping out the Dirac operator for other mathematical tools, like Hodge Laplacians or signature operators. This dead end is known as operator exhaustion. The finite character table of s squared over 2i completely exhausts all basis-independent content. There is no unexplored, hidden geometric operator waiting to be found on this space. Having absolute selectivity and an infinite domain is mathematically insufficient. The inability to find the zeros is not a failure of operator choice, but an impenetrable geometric wall. This split-screen diagram identifies the absolute root cause of this geometric wall, the manifold's positive Ricci curvature equation, where Ric equals 2 over r squared, strictly greater than 0. On the left side, we see the physics consequence. This positive curvature enforces the Weitzenböck bound, a geometric limit ensuring all gauge fluctuations are massive, which creates a mass gap floor and allows physical matter to exist. On the right side, we see the arithmetic consequence. The exact same positive curvature mechanically shifts the scalar Laplacian eigenvalues by -1. This -1 shift mathematically generates an infinite series expansion, known as the Pochhammer tower. The Pochhammer symbol is a mathematical notation used to represent a rising sequential product. When our input parameter s is exactly 0, the Pochhammer symbol equals 0, which collapses the infinite tower. This precise collapse is the exact mechanism that allowed the torsion operator to successfully factor its specific L functions earlier. But at any general value of s, the condition fails. The infinite terms of the tower activate and explode, permanently blocking factorization and shielding the L function zeros from being read. This is the ultimate duality. The very curvature that physically gives particles mass mathematically forbids spectral access to the primes. We can run a theoretical workaround. What would happen if we mathematically removed the Pochhammer obstruction by flattening the space entirely and setting the curvature to exactly 0? Arithmetically, this is a victory. Without curvature, the spectral zeta would factor cleanly across all values of s, finally exposing the precise locations of the L function zeros. But the physical cost is catastrophic. Flattening the space drops the Weitzenböck mass gap to 0. This eliminates confinement, destroys matter entirely, and leaves us with a universe containing no particles to observe. The geometry forces a strict binary choice. We can have a flat universe where primes are spectrally accessible but matter cannot exist, or we can have a curved universe with physical reality where the primes remain hidden. This inescapable geometric divide is what defines the stability principle. We can see this principle at work by comparing the Riemann zeros to the role of the golden ratio within the manifold. The golden ratio is the hardest irrational number to approximate with fractions, and that extreme mathematical stubbornness makes it stable enough to build physical mass hierarchies. Similarly, the absolute inaccessibility of the zeros is exactly what makes arithmetic stable. If a geometric operator could perfectly pin down these zeros, the distribution of primes would be mechanized. This would strip the integers of the computational freedom they require to generate complex mathematical systems. S cubed over 2i operates as a perfect mirror, reflecting the mathematical foundation of reality. It proves that the spectral inaccessibility of the Riemann hypothesis on compact spaces is not a failure of our equations. It is a strict structural necessity for a universe that supports physical mass.